Thank you for coming. My name is Alex, I'm Ukrainian, and I'm a software engineer at Netflix.
And my name is Mykyta, and I also happen to be Ukrainian who works at Netflix, and we came here today to talk about protocols that power gRPC.
That's correct. We came to talk about gRPC, but we want to start by asking you questions. How many of you knows what gRPC is? Yeah, it should be all of you, because this talk is not for beginners. If you don't, you can stay, but it can be not the best use of your time. Who uses gRPC either in production or maybe for your pet project, which is also fine. And what do you folks like about gRPC? I hope not the fact that Netflix or Google or company X is using it. It's not a good enough reason to start using it.
Well, it's not a good enough. Like, why use it then?
Well, it has a lot of great features, and you know those features like API first approach, performance, streaming, and so on. But what makes the difference is its domain-oriented model. It helps you concentrate on getting your stuff done. You operate domain entities, and you don't worry too much about the implementation details. That's a lot of improvement comparing to the old times.
Well, that's right. Do you remember rest time? By the way, who is using rest right now?
No gRPC talk can ever happen without mentioning REST, right?
Well, absolutely. We need to compare those two to compare differences between mental models. In REST, for example, you need to define things like HTTP verbs, status codes, other HTTP details. Don't even try to read it because it's a lot of details and that's just a small part of REST API definition. You need to define ahead of time which HTTP verbs you want to use to create, update, delete your entities. You need to agree how to interpret different HTTP status codes. You need to define the format of your URIs, and by the end of the day, you need to be acutely aware of HTTP itself. On the other hand, let's take a look at a couple of these gRPC methods. On the application protocol level, they are represented as HTTP2 request, but which HTTP verb is used to create a first request? Is it GET? Is it POST? Who knows? What about the second one? Which HTTP status code is returned if the request fails? Does it depend on the gRPC status code itself? You don't even have to think about it. It's not only status code. gRPC gives you generated clients with generated data entities, and the framework does all the heavy lifting for you. Serialization, deserialization, opening streams, managing connections, working with HTTP frames. It's all hidden. The framework already has made all the decisions how to map your RPC models on top of HTTP2.
Which works great until it doesn't. At first, everything looks great, you get performance boost, you get simpler model, but every framework, even the most performant one, can and eventually will hit its limits. And when you start getting unexpected canceled calls, or maybe you start receiving exceptions with deadline exceeded status code, which should not be happening, how do you troubleshoot? Where do you start? Maybe you just want to make your gRPC streaming calls more robust. Should you even be using streaming? And where do you start? The implementation details are not as exposed as in the REST universe. Let's dive into these details. When you use gRPC, most likely you are on HTTP2.
Why do we need HTTP2? Why don't we use HTTP1 instead? Well, HTTP1 has multiple downsides, starting with one dedicated TCP connection per call. It means that one call has to wait for another one to finish because before it can start using the same connection. This problem is called head-of-the-line blocking. And to improve throughput, we need to open more and more TCP connections. And in most web browsers, you have 6 connections per domain. And even on the back end, TCP connections are not an unlimited resource. If you ever had to run ulimit, or if you ran out of ephemeral ports, I feel your pain. I've been there. HTTP2 solved these problems by introducing new concepts. It preserves things like HTTP methods, headers, verbs, status codes, but it changes how data is transferred over TCP. The new concepts here are HTTP2 streams and frames. A stream is a bidirectional flow of data within an established TCP connection, which data is carried over binary frames.
In HTTP1, 5 simultaneous requests required 5 TCP connections. In HTTP2, they can reuse the very same TCP connections. 5 RPCs need 5 HTTP streams, not 5 TCP connections. A message serves as a logical unit of communication, such as your request or response. and in its turn, a message consists of one or multiple binary frames. And what is a frame? A frame is a basic protocol unit with a predefined structure that carries a specific type of data. All frame consists of a header and variable size payload. A header contains basic meta information such as size of the payload, type, flags, stream ID, and the payload itself. Each frame type serves a distinct purpose. For example, data frame carries part of request and response. Headers frame open a stream and carries, well, headers. And what do you think does a go away frame do? Yes, it shuts the stream down. For each RPC, HTTP2 creates a logical stream, gives it a unique ID, breaks down messages for this RPC into multiple frames, labels each frame with a stream ID. For example, in this case, all those frames with blue border will have stream ID 1. And for the next stream, it does the same, and so on. Streams themselves are logical abstraction. On the TCP level, TCP is not aware of HTTP2 streams. For TCP, it's just a bunch of frames. HTTP2 producer sends all those frames that belong to different calls over the same TCP connection, and on the receiver side, frames that belong to the same stream are reassembled into messages for this RPC. In this example, again, all the blue border frames are reassembled into stream with ID 1. This way, streams don't have to wait to each other to complete. HTTP2 improves throughput by multiplexing, sending multiple streams over the same TCP connection. And multiplexing is a superpower of HTTP2.
Well, you know what my superpower is? I always manage to select the slowest line in the supermarket. Even if there's only 2 people ahead of me, it's always the slowest. And a traditional supermarket checkout is a lot like HTTP1. You have to wait for other customers or connections to finish their business before you can ring your own groceries. Next slide, please. You have 5 lines serving 5 customers, and 6.1 has to wait for somebody to clear one of the checkouts. With HTTP2, you can use all 5 checkouts simultaneously. You just mark your individual items with your stream ID as soon as you get it. So if you want to buy some milk, some veggies, some palanitsa, you just mark all items with your stream ID as you put them on the conveyor belt, and you don't have to wait for your turn. On the other end, your recipient just reassembles those items into your personal cart just by looking at your stream ID. And there can be more streams, more than 5, but all of them are putting the items on the connection, on the checkout line simultaneously without any blocking. No one is blocked by a slow customer ahead of them. No head of the line blocking.
Are you sure there is no head of the line blocking?
Well, at least HTTP calls do not block each other, but we'll return to this topic later.
We'll definitely do it. And now, when you know that what HTTP2 frames are, let's see how they power gRPC. Here is a link to gRPC over HTTP2 specification. It describes how different gRPC implementations must translate gRPC interactions into HTTP2 construct. For example, it describes how gRPC request and response map into frames. A request starts with a headers frame, which starts a gRPC interaction and carries a request headers, such as an authorization token or gRPC timeout. Then the message is translated into one or multiple data frames, depending on the size of your request. Response also starts with headers frame. Its payload is also transferred using data frames, and response always ends with yet another headers frame that carries what we call trailers, such as gRPC status code. This approach in gRPC not just paves the way for multiplexing and performance improvement, it also opens the gate for streaming when you can send more than one message during one RPC interaction. We will see how messages for gRPC streaming calls are split into frames. It's very similar to unary calls.
I'm confused a bit. We just discussed HTTP2 streams, and which streams are you talking about now?
I'm talking about gRPC streams. Naming can be a little confusing because, as we all know, naming is hard. gRPC, HTTP2, TCP, they all use words like messages, connection, stream. And in different contexts, they may mean the same or different things. So it's very important to understand what level of abstraction we are on right now when we discuss things like streams. Let's get back to our example. What do we need to do to make it work? To start making this call, to start minting, for example. Well, you all know that we generate Java classes from proto definition, then we create a gRPC channel and instantiate your client using this channel. And channel is a key concept in gRPC. It creates a new construct on top of HTTP2 connection. Channel is a virtual connection from your client to your server, not to a single instance of the server, not to your application server group, but to your service in general. A channel can be backed by one or multiple HTTP2 connections, and it actually manages connections for you.
So to start sending messages through channel, we need to instantiate an auto-generated gRPC client. We need to build a message, and we should finally call the mint method. What happens next? Let's say we have a cluster of mint service instances. A name resolver should determine which actual host we need to connect to. Then the channel should establish an HTTP2 connection. It should open a TCP connection. It should perform a TLS handshake. The client and the server should exchange predefined start of connection frames. Now the connection is open, HTTP2 connection is established, and the client can start sending messages. Mint message on HTTP2 level will be transferred as binary frames, so let's check them out. First, we have headers frame. It starts with stream ID and flags, and then we have headers themselves. First, we have reserved headers. Their names start with a colon. We have things like method, for example, HTTP method is always post, and reserved headers are followed by regular headers like gRPC timeout or content type. And if we have too many headers, if they don't fit into a single headers frame, we can send the rest using continuation frames. Then we may have one or more data frames. These frames carry the actual payload of our mint request message. And data frame also has stream ID and flags. And the last data frame must have end stream set to true, because when the server receives data frame with this flag set to true, it knows that the message was fully sent, and it can start assembling the message for this stream ID. So we have the two frames of the mint request, and the response format is similar. It also starts with a headers frame, which also has stream ID, flags, headers like HTTP status, which is always 200 for example. And similarly to the request, the actual data is also carried over using data frames. We have only one in our case. And finally, we have headers trail that carries the trailers. The last headers should also have end stream flag set to true. And the most important information in these trailers is gRPC status code. Remember, HTTP code is always 200, and gRPC status code is actually the one that contains the actual result of our call.
And this last headers frame must always be sent. Even if status is 0, which is success, even when server decides not to send the response back, for example, decides to fail the request, it still sends this headers frame with gRPC status code. Those frames are useful during investigation. They contain data that we will use during troubleshooting. Of course, all those frames, headers, data, headers, they are marked with the same stream ID. This way, client can reassemble them into one RPC. And one RPC, one call, is carried over one HTTP2 stream. So when you're troubleshooting, what you can do, you can find a frame of your choice. It can be some interesting frame, we'll see it. And then you can note its stream ID, and you can find all other frames in the same stream. This way, you will be able to reestablish the chain of events, chain of binary frames in the stream. And one unary interaction is using one HTTP2 stream. If you're familiar with gRPC, you also know that gRPC supports not only unary calls, it also supports other RPC modes, right?
Of course, yes. We don't have to limit ourselves to a single request response model or unary calls, because gRPC supports streaming. Within a single RPC interaction, we can have 0 to many requests and 0 to many responses. And we can update our mint definition, so we can start minting in a stream. If we add a stream modifier to the request, we get client-side streaming. If we add it to the response, we have server-side streaming. If we have both, streaming is bidirectional. And streaming basically means that RPC interaction is not limited to one request, one response. We can have 0 to many requests, 0 to many responses in the context of a single call. And on the transport level, we're still using HTTP2 streams to represent both streaming and unary calls. And the difference with streaming that we use a single headers frame which is followed by multiple data frames that represent multiple request messages, not just a single message. And we may have multiple response messages as well, carried over multiple data frames. And important thing here is we can disassemble and reassemble those separate messages without sending additional headers. However, just with unary RPC calls, a gRPC stream call is going to use a single HTTP2 stream. And in addition to that, we have other binary frames that we use to manage connections. For example, when a server decides to close an HTTP connection, for example, if it's shutting down, gRPC server is going to send a go-away frame. When the client receives the frame, it starts looking for another instance to connect to for this particular gRPC channel, then it reestablishes a new connection, and it migrates existing RPCs using these new connections. And in less clean version though, for example, if an instance dies unexpectedly, this frame is not going to be sent, so how the client know what to do in this case?
Well, TCP is an idle protocol. By default, it assumes that the connection is alive until proven otherwise. In gRPC, what you can do, you can configure keep alive. Both clients and server can send ping binary frames to each other, and the peer might respond by echoing what they received. If that doesn't happen, the gRPC runtime will consider this connection as broken, it closes RPC, and will start reconnecting to a healthy instance. That's how gRPC maintains a pool of healthy connections, and this is done by gRPC channel implementation. And this is hidden from the developers who use gRPC, from developers like you and me. We can just assume things work out of the box.
Yeah, that sounds great, but we know that things usually work great until they don't. We have so many things that can go wrong here. A client or a server can drop the connection. We have things like routers and switches. Things may get broken there. We have an actual physical wire that can get damaged. All these scenarios will end up in a broken connection. We're going to see a canceled call or connection being dropped, but the symptoms won't tell us exactly what happened. So these are most popular error codes, and some of them may be straightforward enough, like deadline exceeded, but others are more cryptic. When you see cancel status code, how do we know who exactly canceled this particular call? Was it client? Was it one of the servers? When you have an unavailable error, how do you know what exactly happened if metrics and logs don't point us to the obvious problem?
Well, if they don't, we may inspect binary frames to get the complete picture, because as we already know, connection management is also done using HTTP2 frames. So when a server wants to terminate a connection, indicates that it doesn't accept any new connection, it sends go-away frame to the client, which is a graceful shutdown. In normal circumstances, end of stream is indicated by end stream flag on the last successful frame, data for request and headers for response. However, gRPC runtime can indicate an abnormal termination of a stream by sending a special RST stream frame. This frame can be sent by either side, and it implies an immediate full closure of the connection, usually caused by broken connections, corrupted streams, or something similar. Frame contains stream ID and error code. Error code 8 means client cancellation, for example. Also, to verify that connection is alive, both sides can send predefined ping frames to each other. If server sends a ping frame to its client and doesn't receive a response back in a timely manner, it considers the connection as broken, and it ends the stream with cancel status code. If a client initiates a ping request and doesn't receive the ping back, it closes the stream with unavailable status code. So those frames are primary connection management mechanism in gRPC over HTTP2. Now, as we learned about some of the frames, but how do we log them? How do we investigate them? How do we inspect those frames? Binary format is not human readable after all. We need a way to read those frames. But fortunately, gRPC Java, if you're using native, allows logging of binary frames in a human-friendly format. Enabling those logs is a straightforward process. It uses a standard Java util logger. All you need to do is to stop those properties.
And you also don't have to worry about any issues with log4j if you don't have log4j in the first place.
Well, if you do have log4j or logback, you can configure it too. Just say the same log level for this package and install proper login adapter. Also, when you enable it, you will see the logs for the services in your call chain, and those logs can be a little chatty. So maybe consider redirecting those logs into a separate log file so they don't pollute your application logs. To demonstrate binary logs, we wrote a simple application and enabled frame logging. We will see those logs in a few minutes.
Yes, to show how these logs works, we wrote a simple game that simulates minting a cryptocurrency. A disclaimer, no actual crypto is being minted here. It's all fake. So we have a simple backend architecture that consists of a gateway service, mint service, that actually creates new batches of fake crypto, and ledger service that records all the transactions. So when a client makes a mint call, it goes through the gateway, which delegates it to the mint service that creates crypto and then records it using ledger.
Note that even when we make one request, one gRPC request, those streams between services will be different. When client calls a gateway, it's one gRPC stream with its ID. When gateway makes a call to mint service, it creates a new gRPC stream, and ID is different.
Yes, and to debug these streams, we need a way to correlate them. To do that, we can add a tracing solution of our choice, like OpenSensor, or Zipkin, or Jaeger, or something else. So when you instrument your gRPC servers and clients, all the streams in our call chain will share the same trace ID, and we can use this trace ID to find them across the different services.
And when you enable it, you will see a lot of logs like this. So what we see on the stream is one request. One request consists of 3 binary frames here: inbound headers frame, inbound data, and another inbound data. You see all of them has stream ID 77, and the first inbound data frame has end stream flag set to false, and the second one has end stream flag set to true, which means the request message was too large to be carried in one data frame. Also, in the inbound headers, what we see trace ID, because we enabled tracing. We can use this trace ID to find correlated streams for this call. By grabbing this trace ID, we could find 2 streams. One is inbound headers that we already saw, and another one is outbound headers with stream ID 43 in this example. So this is outbound request we are making in the same gRPC flow.
So now we can find all the streams, and we can use the trace to navigate throughout the call chain across all the different services. Now let's use all of this to investigate potential issue. Here is a common scenario. Let's say we have a client that received the cancelled status code with the exception. How do we know which party actually cancelled the call? Our point of entry is gateway. We know that cancellation can be initiated by sending the RST stream frame, and we actually see inbound and outbound RST frame in gateway logs. And the inbound one has an error code of 8, which means client cancellation. So we suspect that client actually canceled the call. And to prove it, let's inspect the stream with stream ID of 21. We see inbound frames. We see headers, we see data, which is a mint request that we got from the client that's expected. And the next frame we see there, it's an inbound RST stream, which means that client canceled the call after sending the request. What about other services? What about their streams? Well, in inbound headers, we have trace ID. We can use it. So we can find the outbound request that goes to the mint service. Now we can take the stream ID 37 and inspect all the frames. So we see that the streams send the request. We see outbound headers, data, and then we see that the stream was canceled. And we can use the same trace ID to find the mint logs, and using the same approach, we see the inbound and outbound RST frames in mint logs as well. So it means that mint service got the cancellation frame and propagated it all the way to the ledger. This is exactly how gRPC cancellation propagation works. It has been proven. It was a client cancellation.
And now let's review another example with the very same symptom. Status runtime exception with cancel status code. You might think it's client again who canceled the call, but let's see if this case is the same. We inspect gateway logs, and this time we don't find any RST stream at all. Instead, what we did find, we found inbound headers from the mint service to the gateway with gRPC status 1. That's a trailer's headers frame. gRPC status 1 stands for cancel status code. So it's either mint service or service downstream canceled the call. We see that this exact frame is from the mint service. You see it's in the frame. And you see status code and gRPC message call canceled. Let's check the mint service log for the stream. You can see stream ID is 17. we see inbound headers, inbound data from the gateway, and outbound headers sent back to the gateway with status code 1. And again, this is min service log, so the next service in our call chain. So min service received the request and immediately canceled this call by sending headers with gRPC status 1. What we can do now, we find trace ID, grab all the logs for the stream, for this trace ID, find outbound headers to the ledger service. This stream has ID 55. We inspect all the frames for stream 55, and we see outbound headers, outbound data, and RST stream. And as you can see, this RST stream is outbound RST stream. It means min service initiated it. So what we see based on inspecting the logs, that min service canceled the call by sending gRPC status cancel to the gateway and sending outbound RST stream to the ledger. So even though the symptoms, exceptions, status code were the same as in the previous example, this case was different. So exceptions with the same status code can happen for different reasons, and they can be initiated in different parts of the request flow. It could also be gateway or ledger. Sometimes, not always, not often, but sometimes you should be able to inspect binary frames to understand what's happening. Frame inspection should not be the first tool in your toolbox. It should not be the second tool in your toolbox. In most cases, you should be able to troubleshoot using exceptions, status code, all the instrumentations that you have, metrics, traces. But in those cases when some of the instrumentation is missing, or maybe all this instrumentation doesn't provide you a clear culprit, understanding how those binary frames work allow you to go one level deeper.
So we showed just a few examples, and for the sake of time, we're not going to try to explain every single status code or failure mode. But you can use the same approach. You can follow similar steps to debug other ambiguous issues using the frame logs, and we explained how frames like go away and pin and others can affect our calls. And the whole thing may sound scary, but in fact, you should only remember 5 different frame types: headers, data, RST stream, go away, and pin. And you also need to know how to find gRPC over HTTP2 specification. It's quite short and comprehensive, and it should explain how to use these frame types. And on top of that, if frame logs, if human readable logs are not enough, you may configure your services to store binary logs of your RPCs and your connection states, and you can use those logs in your automation. Please note that these binary logs are different from frame logs. They're stored like binary protobuf messages and organized differently, but that's probably a topic that deserves its own talk. And that should give us some idea how to investigate connectivity issues. On the other hand, it's better to avoid connectivity issues altogether. We cannot avoid all problems and issues, but we may at least try to optimize the issues related to gRPC performance itself. One big issue is an HTTP2 connection maxing out a number of concurrent streams. Yes, HTTP2 solves a bunch of blocking issues, but it doesn't mean it's perfect. A number of concurrent streams is not unlimited. There is a max concurrent stream setting that controls this limit. By default, it can be as low as 100 in applications with high load or long-lived streaming RPCs. They might see performance issues because of it, and there is a couple of potential solutions. You can just create a dedicated channel for important high-load RPCs. It means that this channel won't get any noisy traffic from other less important calls. It will create a separate TCP connection that will be used just for this channel. It won't get any other RPCs. However, there is a trade-off. If you push this solution to the limit, if you create connection per call, you're going to increase the number of TCP connections between different hosts, and a connection per call may not be the optimal solution. So choose the right area of your application to optimize and use this solution with caution.
Another solution can be to create a pool of gRPC channels. This way you can distribute RPCs over multiple TCP connections, lowering the probability of saturating each connection stream limit. You can either create and maintain pool of gRPC channels yourself, or you can use libraries like Google API extensions for Java or JX Java that already implements channel pool for gRPC. But number of gRPC channels in the pool should be low, otherwise you lose benefits of HTTP2. Using streaming, gRPC streaming could also improve your performance. If you can model your API as a long-lived stream of data, you could achieve a performance win. You don't have to instantiate an RPC every time you send a message. You don't need to send those headers frame between data frames. It removes some of the HTTP2 overhead. However, gRPC streaming has its own trade-offs. Let's check some of them out. If you have long-lived streaming connections, the stream can be idle, which is actually pretty normal. Sometimes you don't know when the next message arrives. And if your streams go through a proxy, proxies are often resource constrained. They may kill idle connections to save resources. For example, AWS ALB default idle timeout is only like 60 seconds. And if you have an RPC stream open with no messages in it for more than a minute, your TCP connection can just be closed by the load balancer, and your RPC stream will fail. To avoid this issue, we may configure keep alive. gRPC client and server will start sending those ping frames. In gRPC, you can do it by sending idle timeout when you instantiate a channel. The keep alive value should be chosen carefully. Unreasonably frequent keep alives will consume your bandwidth and CPU.
And another thing to consider when using streaming is load balancing. If you're using a long-lived connection, regular load balancer is no-go from the beginning because you use the same connection for the whole life of your stream. And timeouts for streaming may not work the way you expect, because in gRPC, timeout or deadline is set per stream, not per message. So if you open a streaming call and you set a deadline of 5 seconds, the stream will be closed with deadline exceeded error after 5 seconds, regardless of the message rate in the stream. Basically, what I'm trying to say, don't use streams because they use cool. Instead, consider the performance gains and compare them to the cost of changes you need to make.
I would say don't use streaming gRPC to optimize performance of your application. Use streaming RPCs to optimize your application itself.
Well,
use it if and only if your application model, application structure, and data flow fits gRPC streaming.
Yeah, I agree, but that's already a lot. Do you want to try this in practice? Because remember, we noticed that we wrote a game and we didn't just write it, we actually compiled the code, we deployed it to the cloud, and Alex is going to show you how game actually looks like.
You think?
Yes, okay. Yes.
Here is the game. It has one button. It requires no skill. That's why I love this game. The button is mint. When I click, it increments amount of fake cryptocurrency. So you see I'm minting just by clicking this button. And on top of the mint button, you see amount that I already minted. And above this amount, you see Chairman Coin 1, 3732, which is my currency name. It's also automatically generated. Also, the top half of the screen contains a leaderboard, top 5 minters.
And we need a leaderboard because we're going to have the competition. We're going to let you try the game, and the most persistent or lucky minter is going to get a Bitcoin.
A Bitcoin?
Well, not a real Bitcoin, like this nice Bitcoin throw pillow. Which
I would play, I mean.
Okay, and you can just go to this URL, mint.grpctalk.com, to try this game. You can use your phone, you can use your laptop. The URL is mint.grpctalk.com, and we're going to use traffic that you generated to actually inspect the binary the frame logs and to prove that we were not lying. Alex, can you switch to the logs, start the login?
I'm just give a few more seconds. Can you play also?
Yeah, sure, of course, I can play. Let's see if I can win.
Okay, so let me enable logs.
Yeah, let's just
collect the logs
from our Kubernetes cluster.
And then what I'll do, I'll just grab random mint request in the gateway logs. I have no grep request. Okay, I have a bunch of them. So let's choose this one, 1463. What I can do, I can copy the stream ID. Oh, I did not copy it. I can copy the stream ID. And now I can grab the stream ID. Maybe I need more lines, right?
No, that's
because, well, many people are playing. Let me do more lines.
You can just stop the logs.
I could, but you see, I needed more lines.
Yeah.
Because I see only one. Did they rotate?
They may, but you can just stop the logs. You can inspect the freshest log again, and because people are going to generate like really large amount of logs, just
I don't know. Did I stop them? Because
No.
let's restart. Live demos are hard.
Yep.
Let's do it again. Can you play?
Yes.
Maybe it's Wi-Fi or something. But while we're grabbing, you see inbound headers. They have different stream IDs.
Can you just do it again?
Sure.
I see that actually people are playing, so I would just try restarting this.
Restart
Pa-
what?
The original command that collects everything from
Logs?
Kubernetes.
I think I did.
Yeah. Like
This one?
I would try it again. Like I would try it for a few seconds, and then I would just stop it, just to make sure we are not like rotating the logs or running out of space.
We are not rotating logs.
Can you just cut it instead of doing tail-n?
I can.
Yeah.
I guess. You want me to cut?
Yeah.
It can be a lot. I think it will be a lot if I cut.
Yeah.
Well, it's not that many. Okay.
Yeah, and I would just stop it. I would just stop it now, just to make sure it's not getting overridden and like, okay, yep.
Okay. Yeah, and now I selected this stream ID, and let's see what we have for the stream, right? Or there's all the requests, and I'll grab the stream ID.
Yes.
Okay.
Ta-da!
Now I see a bunch of headers. Nice. So I see inbound headers, that's a request, inbound data, another inbound data. You see first one has end stream flag set to false, the second one has end stream flag set to true, and also we see a response, outbound headers, outbound data, and outbound headers with gRPC status 1. Okay, that is...
And you get the trace ID and check the mint logs to
That's
see
what
how it looks on the mint side.
Yeah,
because
let's see,
started-
let's inspect this trace now, and I'll probably, let me just do mint logs, right? And then I'll be just grabbing this trace ID. Oh, yeah, I have inbound headers and outbound headers for this trace. So, and you see inbound header is 17585. So I selected it again, and I'll grab mint logs to see what other frames. And I see all the frames again for this request. So
Inbound headers, inbound data, outbound. So
Yeah.
we got the request,
all
we
the
sent
same.
it.
And again, it always finishes with gRPC trailers with status code.
And
Zero.
stream flag of true. So yeah, we weren't lying. I guess we let people play long enough. So let's announce the winner. Let's go
winner?
and check the leaderboard. Okay, can you reload it?
I can.
And the winner is Affectionate Coin 2790. Please find us after the talk to claim your prize. And we also have a prize for runner-up for Giving Coin 4052. We have this Dogecoin pillow, which I guess is a nice prize.
Well, hold on.
Yeah,
Well,
just
yeah.
keep your applications open so we can know that you is really you. And thank you for playing, and thank you for your patience with our live demo.
The difference was very marginal.
Yes.
That's not the end. Oh.
Yes.
Now we got some ideas on how HTTP2 works and how to debug it, but we also see some actual frames and streams, and we discussed some of the limitations, but it's not the end of the story because new season is here. HTTP season 3 has started, and we have to be ready for it. We have to binge it tonight. We need to understand how it's different from HTTP2 and how we can use it in gRPC applications.
First, we need to understand why do we even need HTTP3 in the first place, because HTTP2 solved multiple issues. Why do we even need another protocol?
To understand that, let's talk about multiplexing, head-of-the-line blocking, and our pipes analogy and what's not. There's one TCP connection, and frames that belong to different streams are being sent over this connection. On HTTP2 level, all those frames belong to different streams, they have stream IDs, receivers can reassemble them, but the truth is, on the TCP level, they are sent as one single byte stream. The byte stream is split into different TCP packets, and packets, they have no visibility into HTTP2 streams. For TCP, all those TCP packets just belong to the same TCP connection. What happens when one single packet is lost or delayed? Well, TCP has a built-in loss recovery mechanism, If a sender doesn't receive an acknowledgement, it will just resend the same packet again. Not a big deal.
Why is it bad?
Because first, TCP guarantees in-order delivery, and second, TCP is unaware of HTTP2 streams, which means all packets after the last one have to be delayed. They all have to wait for retransmission. Even though those packets can belong to different HTTP2 streams, they all are resent again, simply because TCP cannot distinguish different streams. From the TCP point of view, they're all the same. They all belong to the same byte stream. And if any of the packet lost again during retransmission, the process repeats. Packet losses and delays affect not one HTTP2 stream, but all the streams that reuse the same TCP connection. And now new streams cannot be opened, they're blocked, this is called
Head of the line blocking.
It's head of the line blocking again. Now it's not on HTTP level, now it's on the TCP level. And if network is bad, multiplexing actually amplifies packet loss. It makes performance worse, not better.
Well, can we fix it with another version of TCP protocol?
Well, TCP is a protocol standard. It's very hard to evolve. It's ubiquitous. It's supported by virtually any device connected to the internet, which means to change the standards, we'll need to update all those devices. Think about all those boxes in the middle, like routers, often outdated hardware. It doesn't sound realistic to update all of them. There's no much choice.
The only other choice then is UDP?
Exactly. It's extremely difficult to deploy another protocol other than TCP or UDP on the internet.
Yes, but UDP is quite lightweight. It doesn't have all these fault tolerance features.
That's why we may need yet another protocol on top of UDP. This protocol would re-implement packet loss recovery, flow control, and other techniques of TCP. This protocol exists, and it's called QUIC. It's based on UDP, which is a stateless protocol itself, and UDP doesn't retransmit packets on the transport layer. So what QUIC does, QUIC implements all those TCP-like properties. It also introduces its own frames, streams, connections. The idea of streams and frames in QUIC is similar to HTTP2 streams and frames. Stream is a communication abstraction, and the data is chopped into multiple binary frames. Frames are sent in QUIC packets over UDP, and multiple QUIC streams can reuse the same UDP connection.
Well, UDP does re-implement a lot of things. Why?
Because this way QUIC is aware of stream IDs, and it also defines its own packets. So QUIC packets contain stream IDs. They're on the same level of abstraction. They're implemented by the same protocol. When a packet is not delivered, when packet is lost, QUIC can retransmit packets only for this one stream. And other streams that exist in the same UDP connection, they're not affected. The protocol will not block those other streams from moving forward. On the contrary, again, with HTTP2 over TCP, streams and packets were defined on different level of abstraction. TCP loss recovery mechanism was not aware of higher level stream IDs. So TCP could not recover packets from one single stream, and that was the source, that was the main contributing factor of TCP head-of-the-line blocking. With QUIC, a lost packet will not end up in a whole connection being blocked. The retransmission happens on the individual QUIC stream, and other RPCs will not be affected by a possible network glitch.
Well, QUIC certainly solves TCP head-of-line blocking issues, and also it's designed to be more flexible because QUIC payload is encrypted, so it's opaque for network devices like switches and routers, and it means that future changes can happen on the QUIC level without having to fix or update those devices, which can just focus on UDP itself. Another key difference is QUIC is a secure by default transport protocol. How does it affect performance? Let's check it out. In HTTP2, to establish a secure connection, you had to establish a TCP connection first, then to perform a TLS handshake, which required 2 round trips. TLS 1.3 improved the situation a bit by allowing to reuse previously cached connection parameters. So when you reestablish the connection, you can reestablish and send the data within the same round trip with no extra round trips. And QUIC took it one step further. If QUIC has already established a connection before, it can also reuse the parameters. But it doesn't have to spend an extra round trip to establish a TCP connection because there is no TCP, so it's true 0 round trip solution. It means that connections are recreated even faster, which is important, especially on slow, on unreliable networks. And another feature for the networks, is connection migration, which comes in handy when you have to reestablish a broken connection, for example, when you switch from Wi-Fi to a cell connection. In fact, connection migration between different networks is a first-class citizen in QUIC. How does it work? Well, HTTP, to identify connection, used so-called address quadruplets, basically the combination of IPs and addresses of both destination and source. QUIC, on the other hand, uses connection IDs, which are opaque blobs that have no specific data that can be observed, and they are associated with the actual network addresses during the handshake. And peers may use more than one connection ID simultaneously, and they may change network addresses that are associated with a given connection ID, or they can even reestablish, request a new connection ID. That means that streams can be migrated simultaneously, and connections are basically not broken, they're migrated.
Those are some of the benefits of QUIC, not all of them, but most of the noticeable ones. But you might be wondering, but how about HTTP3? First of all, as of today, HTTP3 protocol is a published internet standard. You can check on RFC. Here's a link, and it's already supported by the majority of the web browsers. HTTP3 uses the same HTTP semantics, request message, status code, messages, but encoding and connection management are done differently. HTTP3 maps those semantics on top of QUIC, not on top of TCP. QUIC itself includes some features that are also present in HTTP2, for example, flow controls. In those cases, HTTP3 mapping does not re-implement them. It delegates them to QUIC. It delegates stream lifetime, flow control. QUIC has stream with multiplexing already, so no need to re-implement this functionality. QUIC implements flow control, HTTP3 relies on it. Binary framing is similar to what we saw in HTTP2. Framing is also used in the same QUIC streams. HTTP2 frames have the following format. Required fields are just type, size, and payload, no stream ID, no flags. HTTP2 frames had more required fields, but that's because HTTP3 frames, they are already using QUIC streams, QUIC frames. There is no need for another stream ID. Stream termination is handled by QUIC. We don't need end stream flag. This means that flags field can be removed from the generic frame payload as well. If flags are needed, they can be sent in the payload. Frame types, HTTP3 native frame types, are also just a subset of what we saw in HTTP2. Here is a full list of frames that HTTP3 specification defined. As you can see, there is no RST stream, there is no window update, no continuation, no ping. That's because concepts those frames implement in HTTP2, those concepts are done by QUIC now. So there are QUIC frames that are doing it right now.
Yes, but we use some of these frames to implement gRPC, RST stream, and pin. How we implement gRPC without them?
Let's check the gRPC over HTTP3 specification proposal. It's a proposal. The final version may contain some changes, but overall should not be dramatically different. The shape of gRPC HTTP requests and responses, they remain unchanged. With new protocols, there are three significant differences. First is related to error codes, like low-level error codes, not gRPC error codes and HTTP error codes, but the ones that used when connection is aborted, something like that. So in HTTP3 they're different. You will find them in specification. And the second difference is something that we are talking about. The second difference is frame types that no longer exist in HTTP3. Some frame types are just implemented by QUIC. For example, HTTP2 RST stream now is QUIC reset stream. Same with ping and go away. And gRPC will just use those QUIC frames for the same purpose. And also the third difference, HTTP3 requires TLS connections, so connections will always be secure. Most likely there will be no plain text version of gRPC, but in production you should be using secure connections anyway. To summarize these differences, if you know how to make sense of HTTP2 frames, troubleshooting using HTTP3 frames and QUIC frames should not be an issue for you. gRPC over HTTP3 basically means faster connection negotiation with fewer round trips, improved packet loss recovery, and easy connection transition between networks. In terms of implementation, there is one single official implementation of gRPC over HTTP3, and it's for .NET, not for Java, but Java implementation will follow as HTTP3 gains adoption.
So features that we discussed, they definitely sound cool, but there are some things that we should be ready for. First of all, QUIC as a UDP-based protocol. It means that your network equipment and your networking software should fully support UDP. And also, if you use features like zero round trip, you need to know how to mitigate replay attack risk. For example, you can make your request side important. And finally, I cannot emphasize it enough, you should be ready to deal with low-level frames. It doesn't matter if it's HTTP2, HTTP3, or QUIC frames. Understanding low-level details helps you to investigate non-trivial network incidents. It helps you to optimize your application and to scale it better.
And the whole process may sound more complex and scary than it actually is, but once you understand how those frames work, you can use them during your troubleshooting. Also, now we know how to make some of the informed trade-offs to improve our application performance. And finally, as HTTP3 is a new standard, we know what benefits and changes we should be ready for.
So now you can apply this knowledge. You can hopefully see things from new angles, and we hope that it's going to help you to make your application better. Unfortunately, we're out of time. We'd like you to thank you for coming. If you like this talk, please vote for it. If you have some suggestions how to improve it, here are Twitter handles, AI Borysov and Mykyta_P. Reach out to us. We'll be happy to talk to you. And if you do have questions, come find us after the talk. We'll be happy to see you. Again, thank you.